Alrighty then. So this is the completed design for the EvoLabs EV-1. And those familiar with Fusion 360 will notice that yes, it's designed entirely in Fusion 360. And this was quite a tedious, lengthy process. But I've discovered, through experience, that when you have a relatively complex product that you want to build, that actually designing the individual components first in a CAD software and joining them together, interacting with them, is just a much more effective way of actually designing and building anything. So I designed or drew the parts, nearly everything except for bolts and wiring, but essentially everything that is required for the printer I designed, and either designed myself or imported as models into Fusion 360. So the overall dimensions are 596 millimeters high by 681 millimeters long by 491 millimeters wide. So it is a fairly substantial printer, and the reason for that was that I thought, well, if I'm going to build my own design 3D printer and not base it, own custom design that's where all of the primary parts are actually designed from scratch, then I might as well make it a big printer to make it unique, rather than a cheaper, easier option would just be to buy a kit set of an i3 style printer. So the frame design is based on 2020 profiles for the horizontal parts, of horizontal frame parts, and 2040 profile for the four vertical parts for the box. I actually originally first tried to use exclusively 2020 profile because it's cheaper, but the frame just doesn't have the rigidity, especially as you scale it up in size. So zooming into the corners of the frame, you'll notice that I'm using these brackets, large brackets on the outside of the frame and smaller brackets on the inside. And I don't recommend that you would do this if you actually build a frame of this type. And the reason is because it requires a lot of brackets and it's very fiddly. Most of the brackets are 4 bolts each, which means you need 4 bolts each and you need 4 nuts each to put into the frame. It's tedious work. The better approach is actually to have self-tapped holes drilled into the profile and then bolt them together that way. But as you can see by this corner area, I didn't have long enough 2020 profile to cover the entire area for at least one side of the frame, and so I ended up just using brackets all the way around. It does work, it's effective, it's rigid enough, but it is quite tedious to do. For this design, the maximum dimensions in terms of the z-axis was limited by the height of available threaded rods. In this case, I ended up using the 500mm threaded rod. I think there are longer threaded rods you can buy, but with this design whereby the hole at the top here is it's a gap essentially for to protect the end of the threaded rod. It's not actually a bearing, so your bearing point, or your point of rotation if you like, is actually at the stepper motor down the base. So you get a lot of wobbly movement and a lot of stress on the join or the joiner for the stepper motor to the threaded rod. So I limited it to 500mm. So you have a maximum theoretical z-axis height of 500mm. In terms of the other dimensions, I guess one of the unique things about this compared to your typical i3 is that I'm using V-slot linear rails rather than smooth rods with linear bearings, and that means that you can get much longer lengths of travel than you can with your average linear rods, your smooth rods. I found in practice that using the smooth rods at anything above about 350 mil, they just don't have the precision in their length to be able to effectively use them, especially in the z-axis. So by using these V-slot linear rails and these little Delrin mini wheels you can see modelled here, you can have a much larger printer and a much smoother movement in the axes. So in terms of the plastic parts on the printer, which, for example, the controller display housing, the controller board housing, most of these grey parts, except of course the power supply, these were all printed in either PETG or ABS, mostly PETG, but for the extruder parts here, they're all in ABS to withstand the higher temperatures that the extruder puts out. I think you possibly could get away with using PETG on everything, but I just went for the safest option, which is to use ABS for the extruder parts. Now what is a little bit more difficult to see because I didn't model it, and that is the belts. So if we look at the y-axis, that's where the belt would have been, straight through there. And I ended up using 9mm wide belts, timing belts, rather than the 6mm. And I found through experimentation of an early sort of prototyping of the frame that the 6mm belts, under tension, they just didn't behave as well as I'd like. So I went with a wider 9mm design, and I'm really happy with that. I think that's probably the better option as you scale up your printer size. I wanted to simplify tensioning the belts for both the x-axis and the y-axis, so I came up with this system of a sliding part in a housing and with these peg holes here. Those peg holes extend all the way through the housing. So the idea is that you slide this part, which includes the pulley, you slide it backwards, and then when you have the desired tension on your belt, you just push through a 3mm bolt through the peg hole, down through the housing, just reposition this correctly, through the housing, and then you would also put a nut on to tighten it to secure it in place. And I've also applied that system for the y-axis, and here is the equivalent part there. You can see the two parts on the side of the idler pulley, then slide through this housing here, and we have the same type of 4 peg holes, which also extends through the housing. The controller display I'm using is the same type, or a generic type, as used on the Prusa Mark II, and it's a RAMPS LCD 2004. It has an SD card reader, the typical rotary encoder, and is a simple 20 character by 4 line LCD display. I elected to go with the simple controller rather than a graphical display, simply because I'm more familiar with it and it's going to require less programming than a graphical display. So I went with a entirely 24 volt system, including use of a genuine E3D 24 volt extruder, and I'm using a 350 watt Meanwell power supply, as I said, running at 24 volt. Meanwell are quite well known as being decent power supplies for 3D printers, and I chose 24 volt rather than a 12 volt, a cheaper 12 volt system, is because basically with a large bed size, it's 330mm square bed size, you really need as much power as you can get in order to be able to heat up the bed, especially at higher temps, within a reasonable time frame. So I also decided I wanted to use a cable chain system for managing wiring that's attached to moving parts, i.e. the bed and the extruder, or the X-carriage, and I decided that I would design and print my own cable chain links, which you see here. These are actually fairly tedious to print, and I'm not 100% happy with the design, but it does appear to work in practice when I prototyped it. I may actually in the future use the standard cable chain design, or purchase the standard cable chain that comes with CNC machines, But in this case, what I've done with my design, if I zoom in here, on the X carriage I actually have this custom attachment point and also a custom attachment point for the bed. You can see here. So I'd have to redesign those if I wanted to use a standard cable chain that you can actually purchase. So something that's probably different from most i3 style printers is that I've chosen to mount the X carriage stepper motor in the vertical rather than the horizontal, and that's something I used in my prototype and it seemed to work quite well. I didn't notice any downside of that approach. And in this case, because I'm using the V-rail, it means that it's more compact in many respects than if I were to mount the stepper motor in the horizontal, and it means that the entire system of the stepper motor and the belt is at the rear of the X carriage, and it also meant that I had to design the belt holder in relation to the X carriage and the Delrin mini wheels. So in practice we'll see how well that's going to work, but as I said, my prototype at least suggested that this will be a viable option. If we zoom in on the extruder body here, you'll notice there's these large holes, and so what I decided to do was to come up with a design to actually reduce the profile of the extruder idler tensioning bolts. So instead of the bolts coming through the right hand side with the springs on the outside of the body, as per the likes of the Prusa Mark IIs, the bolts are placed inside of the extruder body, then secured in the normal way with these square nuts. And so that results in a lower profile overall because the bolts aren't sticking outside of the extruder body. So if we take a closer look at the extruder body, basically the extruder housing, it's very much like the Prusa design. I did try to come up with an optimized cooling fan shroud, if you like. And this is based on something I did with my prototype that seems to work quite well. The other thing I did was, if we zoom in on the space here for where the filament is directed, as well as having a block area here for where the PTFE tube is inserted, I've also added an additional block at the top of it, essentially as a mirror of the bottom part. Because what I found is, often when you insert the filament in the Prusa Mark IIs, unless you had the filament really straight, it would veer off and you would have trouble actually inserting it into the PTFE tube at the bottom here. So by reducing the amount of free space for the filament, I'm hoping that it will actually be able to direct the filament more consistently into the PTFE tube without sort of misalignment. So here is the power supply case housing, if you like. This is printed in PETG and is secured to the frame via these brackets, and it's important to note that it's flush with the frame, with the exception of the switch, on the basis that we're going to actually put walls on this printer at some stage in the future to make it fully enclosed. I'm not 100% happy with this design of how I've actually done this. You see, I've got a bracket here and I needed to add this bracket. The original design didn't have this other bracket here, but of course without it, when you push in the plug, the IEC plug, it flexes on the brackets. So on the frame brackets. So this additional bracket here with a bolt hole going through it, just make sure that you can actually insert the plug without it flexing the housing. This case here is for the controller board. See, I've got these cooling holes on it, and it's fixed to the frame very much like the power supply case. And at the top there's a hole for the USB cable and the reset button. And the controller board I'm using here is the Mini Rambo 1.3 controller board, which is the same used on the Prusa Mark IIs. So it's a fairly familiar board in use. It's important to point out the reason for the close proximity of the controller board housing to the LCD display, and that is because these use ribbon cables, and ribbon cables have, I think it's a theoretical length of about, maximum length of, I think 300 millimeters, and so you really want to make the distance between the display and the board as short as possible, otherwise you'll get the potential for electromagnetic interference, which will then negatively affect the actually LCD display. You may get weird characters and have to keep refreshing the screen. So that's why these are so close together. So the stepper motors I'm using are the standard NEMA 17 type, and as per a standard i3 I have 5 of them, 2 for the Z-axis, 1 for the X-axis, 1 for the Y-axis, and the extruder stepper motor. So the inductive proximity sensor used here is very similar to the Prusa Mark IIs. The model is LJ83-2-Z/BX-5V for 5 volts. So it's a M8 2mm sensing direct current 5 volt NPN type, and that's obviously used for automated bead leveling, which I'm achieving using the Marlin firmware. So initially I faced choosing to have a large bead size, so 330 by 330 mm square bead, was that I couldn't actually find a bead frame that I've shown here that matched the heated bead. It's easy buying the heated bead of that size, but actually finding a available bead frame, I just couldn't find one. So what I ended up doing was just simply buying 2 of the same type of heated beads and then cutting out these slots to lighten the weight of it, and also to drill the necessary holes for the pulley housing and the Delrin mini wheel bearings. And it's important to note that as you get up in size with your bead, that you're going to face issues of inertial mass, and with a bead this size you want to keep your inertial mass as low as possible to reduce the vibration on the printer and help reduce sort of negative artifacts on your prints. As a consequence of this large mass of the bead moving back and forth